So I was going to start off with a quick recap of the network we built last week. I'm going to keep it really quick because we're a bit short on time. So this is just a brief reminder of the different network layer types. And apologies to the people who missed last week and might be a little bit lost. Videos are all on YouTube, so you can catch up if you want to as well. So this was the kind of vanilla layer, the densely connected layer that we use for sort of standard tasks. But if we're using image processing, we usually use convolutional layers like this one. So then Alison talked a lot about this, but basically the neurons are arranged in blocks and each block looks at only a small receptive field. The max pool layer is also used a lot in convolutional networks. The reason for using a max pooling layer is for regularization, so it kind of smooths your data. So basically in this little quadrant here, you're just taking the max value and the same in this one and so on. And that's just to smooth your network layer out a bit so that you're not too reliant on your training data. So as Alison mentioned, deep learning is very prone to overfitting, so it means it doesn't generalize well to new data that it hasn't seen before. So this is just a method of preventing that. And the dropout layer is one other way to do regularization. It's not particularly intuitive, but the idea is that during training you randomly just get rid of some neurons, choosing them randomly. And the reason for that is if this neuron is, for example, in a face detection algorithm, if this one is detecting an eye, maybe the network is becoming very reliant on finding the eyes in order to detect the face. So if you just drop out that neuron, maybe the one next to it has to work a little bit harder and it learns how to detect noses as well, for example. Okay, so those are the network layer types we met, and this was the network that we built last week in Tensorflow. And this evening is going to be all about Keras. Keras is a higher level API than Tensorflow, so it actually sits on top of Tensorflow or other backends. And I wanted to show it to you because it's a really nice way if you want to build a network quickly and if you want to build a network easily, and you usually do want to do quick experiments with deep learning because you want to try lots of different things to see what works best. Keras is a really quick way to throw networks together much more easily than TensorFlow raw, in my opinion. So TensorFlow is great if you really want to be in the nitty-gritty and you want to have access to all your weights and biases. Maybe you want to try a different layer type that hasn't been invented yet and you want to figure something out, then use raw TensorFlow. But if you're just using layers that already have been invented, let's say, then you can use Keras. So this is the network we're feeding in MNIST data. These are handwritten digits and they're represented as 28 by 28 images. So our input to the network is a 28 by 28 by 1. If this was a color image, it would be 3 at the end. It's a grayscale image, so we just have one layer thickness. And I don't want to go through too much detail. We do a convolutional layer on this, and we output 32 filters. So as Alison mentions, the 32 is the number of features that we're detecting in this first layer. We also do a max pool there. That's how we get from 28 by 28 down to 14 by 14. We follow that with another convolutional layer, which has 64 filters, and another max pool, which brings us down to 7 by 7. And then at the end, when, as Alison mentioned, we've kind of extracted all of the features that we're interested in, we can flatten them out and try to figure out which features make up which kind of digit. So our final output is a 10 by 1 array, and it's what's called one-hot encoded. So that means that if the 0th element is 1 and all of the others are 0, then we think that the number was a 0, the number that was in the image we input. If the first element is 1, then we think it's a number 1, and so on. And we finally have a softmax layer that just makes our output probabilistic. So in other words, we have maybe a 90% chance that we think it's the digit 5 and small probabilities for all the others. Okay, so that's the recap on everything that we did last week. And now I want to move on to Keras and hopefully make you believe that you should use Keras to do this next time. Okay, so what is Keras? It's an open source library. It's the brainchild of a guy called Francois Chollet, who works in Google Brain. He developed it quite a while ago. I'm not actually sure if he was even at Google Brain at the time, but it's become very widely accepted as a really useful tool. It's purely in Python, so you don't have to worry about a lot of stuff if you're used to writing in Python. And it can sit on top of lots of different backends. So TensorFlow is one backend you can use. If you're used to using Theano, you can still use Theano as a backend. Same for MXNet, CNTK, and so on. Why would you use it? It allows you to build model architectures really quickly, and I'm going to show that most of this presentation is actually going to be code snippets to show you the difference between writing TensorFlow code and writing Keras code. You don't have to worry about handling the TensorFlow session, which can be a bit messy. We saw last week that you have to kind of build up your graph first, and then nothing actually happens until you start a session, and then you run the session. You have less keeping track of matrices, what sizes they should be, because Keras keeps track of that for you, and you don't have to manage the sizes of the weights and biases and all of that. which can be a disadvantage, as I mentioned, if you want to get into the really nitty-gritty and you want to do minute things with those weights and biases that are not usual, then you probably want to go back to raw TensorFlow. Before we dive into the code, just to mention that there's really good documentation at keras.io. That's the best documentation for any API you could imagine. Since 2017, Keras has been integrated as part of TensorFlow Core. So in other words, if you've installed TensorFlow, then you already have Keras in there. You can still put Keras on top as a top layer if you want to. There's no particular reason if you're using TensorFlow why you would do that. All the calls from the TensorFlow Core are the same as from the external Keras API. If you do use it as part of TensorFlow Core, don't use the TensorFlow documentation because it's very basic. Go back to the Keras documentation, it's much better. And just to mention, the Keras has a large user base and really good online support. So if you're having any problem and you Google it, you're going to come up with lots of answers. So like Stack Overflow has 12,000 results from searching in Keras. Okay, so this is code that we ran last week, and actually we didn't have time to go through it in detail last week, but this is the code to write 2 convolutional layers in raw TensorFlow. So we first defined a few convenience functions. So you see here that, I don't know if you can see it. So TensorFlow does have a conv2d function, but in order to always pull that with the same strides and the same padding, we made a sort of a convenience function for that. We had to write a function to get weight variables of a certain matrix shape, to get them to be randomly distributed from a random distribution, because you never want your weight variables to be initialized as constant. Your biases, again, have to be initialized. We initialize them with constants, that's okay. We have another convenience function to do that. And then we have our first convolutional layer here. And so we tell it what size the weight variable needs to be, that we're going to have an input size of 1 and an output size of 32 in this first convolutional layer. We have to tell it what size to make the bias matrix. Then we have to tell it to do this conv2d with the input image and the weights and add the biases, and then do a ReLU on top of that. And then we have a second convolutional layer, and we have to keep track of, well, the last one, output 32, so we need an input of 32 here, and then we want an output of 64, and so on and so forth. So it's a bit convoluted, and it's a bit not terribly intuitive. In Keras, we can do this really quickly. So these are the imports that you use if you're using the Keras inside TensorFlow Core. So we just import this thing called sequential and something called conv2d. And we set up something called a model. So they have this model object, and it's a sequential model is just the most basic kind of neural network. So sequential just means we're going to add one layer after another in sequence. And then we just do myModel.add, and we add a conv2d. And in this conv2d, you specify the input shape. You only have to do this once in a Keras model. You just tell it the input on the very first convolutional layer, and after that it figures out all the sizes thereafter that should be output and input to the next one. You can tell it the kernel size, the number of filters that you want, the padding and the activation function all within the one line. And again, you can add a second layer very quickly. We don't have to tell it that the input to this layer will be size 32 because it knows that already through the model object. Okay, so now looking at adding a dense layer. Again, this was the raw TensorFlow code that we used last week. We had to keep track that when we were adding our dense layer, the input size was 7 by 7 by 64, based on what was coming in from the last layer. And we tell it that the output needs to be size 1024. We have to set up our matrix of weights and our biases. We do this tf.reshape to flatten it, because before we can add a dense layer, we have to have flattened input to it. And then we have to do the matrix multiplication, add the biases, and then apply the ReLU to it afterwards. In Keras, we can do it in 2 lines. We just do myModel.add and then a flattened layer, flattens, and then we add a dense layer. And we don't have to tell the dense layer what size input to expect. We just tell it what size output to spit out, and Keras will figure out what the input is going to be. And we tell it the activation function. Okay, so this is all code snippets showing how you can do TensorFlow versus Keras and how much quicker you can do it in Keras. This is the loss and the optimizer. In TensorFlow, I think it's very unintuitive how you do it. So you set up cross entropy. You tell it that you want to average the cross entropy over the batch, which is usually what you would do. And then you have to tell it in a training step, I want you to use the Atom optimizer, which is a kind of optimizer to get low down in your loss function. And you have to tell it explicitly, I want you to minimize this loss thing that we've already calculated. So it's a bit complicated. In Keras, we just use something called compile on the model that we've created. And we just tell it the name of the loss function we want to use. In Keras, it's named categorical cross entropy. the optimizer we want to use, and the list of metrics that we wanted to calculate along the way. So it always calculates the loss, obviously, it has to calculate the loss, but you can give it extra metrics. So in this case, I've put in accuracy, and you can put in a list more if you want to keep track of other metrics along the way. The training, this is the loop for training in raw TensorFlow. We did 20,000 iterations over batches of 50. We put a special print statement to print every 100 steps what our accuracy was. And then you do train step.run, so this is inside your session. And you feed in, use this feed dict syntax to feed in a batch of 50 samples and a batch of 50 labels, and the probabilities to keep neurons in your dropout layers. And with Keras, you can do it in one line. You just do myModel.fit, and you give it the data to fit the model, to fit to the model. So you feed in the training images, the labels for those images, you tell it how many epochs to run for and what batch size to use. Just to point out that epochs in Keras is not exactly the same as iterations in TensorFlow. There's a relationship between them. So in Keras, epoch means go through the entire data set one time. So that's 55,000 images. So I've put a little note here of how you can relate back if you want. So in this sample, in this network, we showed 1 million samples to the network. So I've just set epochs at 18. It works out that that will show 1 million samples to our Keras network. And then for the testing phase, again, in TensorFlow, you have to tell it how you calculate accuracy. You have to compare the argmax of your prediction with the argmax of your true label. If they're the same, then it's a correct prediction. You have to tell it to average over the mean of all of those. And then you have to feed in your data to calculate the accuracy on the test data. Again, in Keras, we can do it in one line. So we take our model that we built and we call something called evaluate on it. We give it the test images and the test labels. You can give it a batch size. The batch size in testing cases purely just to stop it. If your data set is too big to fit in memory in one go, it'll do it in batches. Okay, so to finish off, this is the code that we used last week on the left in TensorFlow, and this is the equivalent code in Keras just to build, train, and print the accuracy of our network. So you can see there's other code around it, but this is the equivalent code on the left and right highlighted in red. So that's how much faster you can put a network together in Keras. Okay, so the code is all on GitHub. So anybody who wants to go along with the hands-on tutorial, if you go to github.com/corkAI and Meetup 2, there's a bit at the start which I skipped past. It was just looking back at the network we built last week. I think because we're a bit short on time, we'll go straight ahead to the Keras one. So if you have any problems with AWS, as Peter mentioned, Chris from AWS is here. He's based in Cork. He's our local AWS guy if anybody wants to talk to him about anything AWS. And if anybody's having problems with their account or can't access the GPU compute machines, just have a chat with him. He's over at the very back over there. Otherwise, you can go straight ahead, sign into the console, and launch your instance if you can. If anybody's having trouble, just give myself or Peter or Chris a shout. So once you get logged in, you can go ahead and train the network just as we did the last time on the MNIST data, so on the handwritten digits data. And you should get about 99% accuracy. And once the network is trained, then the next exercise is actually to test it on some handwritten digits that I hand wrote myself. This was an additional exercise last week if anybody got to it, but I don't think many people did. The idea is to show that if you handwrite digits yourself and they don't come from the same source as the MNIST data, that you do not so well on them when you come to the testing stage. So some of them were photographs of digits written on paper, which is actually very different from a digit that's written digitally. Okay, so if you got to the end of training, it's about 99% accurate, which is really good. But this is a really basic benchmark data set where you expect to be really, really good. So don't get too excited.
Sorry, you were saying that this doesn't apply well to new data. So it's only good at predicting the data you're training.
Well, what I'm about to show, I'm not going to go through all the steps in the tutorial just in the name of time. I'm going to do here's one I made earlier. So somewhere in here. So these are the images, some of them that we put in. Sorry, this is all in GitHub, yeah, and all the instructions how to do it is all in GitHub. So this is a photograph of a number 5 that I wrote on a piece of paper and photographed it and then inverted the colors and made it 28 by 28 so that it fits in. And as you can all see, it's a number 5, but the network predicts it to be a number 3. So
Number 3 and 5 are kind of close.
they're close enough, yeah. It's, in fairness, like, yeah. Yeah, so the idea here is to show that because this is a photograph of a digit from a piece of paper, which the training data wasn't, the training data was truly digital data. Exactly. You can see here that there's a kind of a shadow or a light effect from the photography. This is another photography example, so you can see again the shadow effect, which it wouldn't be used to from its training data. And this is a number 8, which is predicted to be a number 3. So it's not good at photographs. And this is a number 9, which is predicted to be a number 2. But again, you can see all the effects from the kind of paper it was written on or whatever. Yeah, exactly. It's dirty looking. It doesn't come from the same nice clean data set. I also made some images that I just wrote digitally on the screen, white on black, which looks like this, and it does a little bit better at that. So this is a 2 and it predicted it to be a 2. So it's cleaner, it doesn't have the shadows from the photographing and so on and so forth. This is another digital one which it correctly predicted to be 6. And the last one is a 9, but it thought it was a 2. So, but you see the challenge is that if you take data from a different source and it's not exactly similar to what it's used to and what it has seen before, the MNIST data all came from a sort of a protocol of how to write the numbers or whatever, so it was all done the same way.
It's a small
This is a bit different.
If you had like a massive data set of, a more realistic data, then it might do a lot better.
If your massive data set included photographic images, for example, but it doesn't matter how many MNIST digits you give it, it'll never do well on photographs, no matter how many hundreds of thousands you give it. If it hasn't seen photographs before, it won't do well on them. So that's the kind of moral of the story for today. There's also an exercise on there to do the same thing with these fashion data. So the fashion data is a little bit funny. This was a coat which it predicted to be a pullover. This was a failure on the network's part. To be honest, I think when they rendered their fashion items down to 28 by 28, they lost a bit of information. Yeah. But the idea is there to show that, if your data is not as easy as MNIST, then you don't get such good results.